Okay, so this is homework 2, part B, where we're going to be using the differential energy balance to derive the heat diffusion equation for cylindrical coordinates. So we'll start here. We have our cylinder. We have heat flowing in and out. And so I kind of cut it here. Uh, right, so we have our R, right? That's our radius. And then we have our Z. And then the third, so like in the Cartesian coordinate, we had X, Y, and Z. Our third dimension here is going to be theta. And so theta is this value here, right? That's our theta. And so when we look at this, I'll actually draw this out so it's a little cleaner here. Um, sorry. Right, so nope, this is our pipe here. And when we look at this, right, what we're going to be looking at is this section here, actually. Um, and so it's like our extension. And so this is our X, right? And so our Z value will be this here. So down here is Z, up here is DZ. Our R value is this value here, right? So we have our R, and then we go to our dr. And then our theta, our d theta is through the middle here, right? That's how it extends, right? So when we're looking at our volume, right, volume equals, and before we had x, y, and z, now we have d theta, dz, dr, but theta is not in the same units as z and r, right? So to get that to be compatible, we have to multiply by our radius again. And so when we do this, we're able to then move on like we did with the Cartesian coordinate. So we had 3 equations for Cartesian coordinates, right? We had our energy storage, which was our rho C, right? Our density times our heat capacity times our temperature over our change in time times our volume, right? So our R, d theta, dz, dr, right? And then we had our energy generation, Eg equals our heat flow, our change in heat flow times our volume, right? So our R, d theta, dz, dr. And then last we had our energy balance, right? So we had E storage, right? Our energy storage equals our generation plus our net heat flow for each of the 3 directions, right? Our theta, our z, and our r, right? So we'll have our net heat flow of z plus our net heat flow of r plus the net heat flow of theta, right? And so when we look at this, well, right now we do not have any of our net heat flows, right? We have our EST and our E generation, right? So how do we do that? We do it with the Taylor series expansion, right? So I mean, when we look at that from before, we know that we look at um, our Q of our. We'll start with our Z, right? Our Z term. I'm actually going to move this down. So we'll start with our Z term, right? We have our Q dz is similar to QZ minus plus dq over dz evaluated, right, from our where our new equals our old times dz, right? And so when we look at this, we know that our net heat flow equals Q in minus Q out. So when we plug that in, our Q in for in the z direction, it just QZ minus our Q out for the z direction is our QDZ, right? So we take this expression here and plug it in. We get QZ minus the change in heat over the change in position, where dz equals z times dz, right? And so we can simplify this, right, down to dq dz or dqz over dz times dz, right? And so this is our net heat flow in the z direction, right? And so we can repeat this process, and like we did for the Cartesian coordinates, and for this one here, we just do the exact same principle for our r direction and our theta direction, right? So it's q dr is similar to qr plus d, our change in heat over our change in radius, dr equals r dr. And then that follows the same principle here and then down to here. So we get our net heat flow of R equals minus dqr dr dr, right? And then we can do the exact same thing for theta. Q d theta is similar to q theta plus the change in heat over the change in theta, evaluated d theta equals theta d theta, right? And then that, again, exact same as up here and up here. We just, our net heat flow for theta equals minus d q theta d theta d theta, right? So now we have our net heat flows, but we need to figure out what q theta, qr, or q theta, qr, and qz is, right? These values here. So how we can do that is using Fourier's law. So when we use Fourier's law, right, for example, in the z direction, right, qz equals minus ka dt d theta, or dz, sorry, right? So our a, right, we have our z direction here. So when we're coming through, we have our change in theta and our change in r, right? Those are our two other values that we do not account for when we're, so that has to be our area. So then qz equals minus k times our new area, right? So d theta dr dt dz. But like before, theta is not in the correct unit. So in order to change that, we have to multiply by our r, right? And we can do that for each of our net heat flows here, right? So we have our qr equals minus k. And then for this one, we have our r, so we need our z, right? So we have our r d theta dz times dt dr. And then here we have our qr equals, or our q theta equals minus k. And we have our theta here, so we do not need this r d theta value. So we have dr dz dt d theta. And so then we can plug all these values into these equations here, right? So we have our d sorry, we can uh, we can plug these in, right? So for Z, um, I'll bring it up here. We'll do it up here as we go. So E storage, right? We have our rho CT dt times our change of volume, right? So R d theta dz dr equals our Q times R d theta dz dr. And then we have uh, our net heat flows, right? So I'm going to put this on another line so that it's a little easier to see. But um, so our net heat flow of Z, right? We have our dz times, and this is our minus. These are all going to be minuses, right? We have our minus sign on each of these. And so that will cancel out with this minus sign in our K. So it's going to be d dz K times R d theta dr dt dz dz. And then we do the exact same thing for the next ones. We have our d dr K times R d theta dz times dt dr times dr. And then our last one is our theta. We have our d theta times our thermal conductivity times dr dz dt d theta times our d theta. I have to squeeze that in here. So when we look at this whole equation here, right, there are a couple of things that we can cancel out, right? We have our volume term in each of these, right? So we can cancel out everything that in this parentheses except the R, right? So we leave the R in each of these because our R can't cancel out in these equations down here. But we are able to cancel out the d theta, dz, dr. We do that for each equation, which then simplifies it down, right? We have our rho c t over dt times r. And we can change this to rho c, change in temperature over change in time, right? Times our r, that's not a capital R, times our r equals our q times our r. And then when we simplify all these, we then get plus d dz kr dt dz plus d dr times k r dt dr plus d d theta times k dt d theta, right? And so what we're looking for at the end of this equation, right, that's going to be our dt dt value, right? Our change in temperature over our change in time. So how we get that alone, we have to divide by our rho c and our r. When we divide by our rho c, these terms all have this k value, right? Well, k over rho c, right, our thermal conductivity over our density times our heat capacity, that is our thermal diffusivity that we have talked about in the other videos, right? So I'll factor that out. And then we can divide by our r, right? So we can get rid of this r. We can get rid of this r. And then we will have a 1 over r on this side. Now, it's important to note that this r we cannot get rid of because when we look at this equation, the derivative is with respect to r. So if you got rid of it, you would be changing the equation because this is a product rule, when you do the derivative. So when we rewrite this equation, I'm going to go to a new page here. We get, right, we have our change in temperature over our change in time, right? That equals, when we go back, right, we'll have our thermal conductivity factored out. So our alpha equals d dz, right? That's our first term, times, and we cancel out our r, so then times dt dz, right? Our change in temperature or change in position in the z direction, plus our r value, or our dr, so it's d dr, right? But we have to divide this whole thing by r. So we'll start with a 1 over r times d dr r dt dr, right? So this is our new r term. And then we can move on to our theta term, which will be a 1 over r, right? Because we didn't have that r term in the theta term because we didn't need to account for it in our area, right? So that r term is new. And then we can multiply by our d theta dt d theta. So this is our new equation, right? And when we do this, actually, I'm wrong here. So this will be an r squared because when we canceled out our dr, dz, and d theta, right, we also divided by this r, right? So this is then a 1 over r. So that in turn makes this a 1 over r squared when we divide out the r from the other side. So then when we look at this, right, this is technically our final expression, but we can simplify it, right? So when we look at it, ooh, I missed our Q, our heat over our density times our heat capacity. That's from this earlier part here. We only canceled out the R, not the Q as well. And we have to account for the density over the heat capacity, or the density times heat capacity. So we look at this. This is just a second derivative of each of these terms, right? We have our dt, to simplify this down a little bit more, our dt equals our theta, or our alpha, times the second derivative of temperature in the z direction, plus this term cannot be changed, 1 over r d dr r dt dr, plus 1 over r squared times the second derivative of our temperature in the theta, right? And so this is our final expression for the 3D heat diffusion equation in cylindrical coordinates. So from this, we'll move on to the next part of the question where it gives us, right? So I'm going to copy this so that I can mark it. Okay, so we have this equation, right? The question gives us that there's no, I again forgot my Q up here. Right, so we have no heat generation according to the question. And we're also at steady state, so that equals 0. And when we look at this, it's only asking about the radial direction. So we can negate these terms here to where we look at our equation and we get 0 equals 1 over r d dr R dt dr. Right, so this is our equation. Now, when we look at this, we can get rid of this, right? Multiply by r times 0, 0, right? So 0 equals d dr times the derivative r dt dr, right? So we want to be able to solve this when looking at any specific radius or any specific temperature. We want to be able to get those values. So to make that a little easier, we're going to relate this r dt dr to a constant of integration. And then when we look at this, right, we can do it dt dr equals c over r. We can integrate both sides. This is from our T initial to our temperature final, and this side is from our initial radius to our final radius. So when we do that, we get our temperature final minus our temperature initial equals our C times the natural log of, it'll be times the natural log of R final minus the natural log of R initial. Now this can simplify down to the natural log of R final over R initial. So when we do this, we can find that C equals T final minus T initial over the natural log of R final over R initial. So then we can come back up to this equation here, and instead of going all the way to our final temperature, we can pick whatever temperature we want, right? So we have our T initial 2T, right, of dt dr equals, and then we have our initial radius, and then the radius at which this temperature is at of our C over our R. That then makes this integral T equals, or T, our temperature as the spot we're looking at, times or minus the initial temperature, equals our C, this is just R, our C times our natural log of R over R naught, right? Using the same thing that we did up here. Well, we know C, right? So T minus T naught equals what we just found for T, right? So T final minus T initial over the natural log of R final over R initial times the natural log of R over R naught, right? So we can look at this, and we want to know what our temperature is. So we can just do T equals, and then it's this whole term, right? So TR minus T naught, ln R final over R initial, ln R over R naught, plus T naught, right? I'm going to change this term here back to C, just so it's a little easier when I'm writing everything down to explain things. So C, right? And now we want to take our derivative, right? So dt with respect to R, dr equals our C, and then derivative of this is just R over R naught times 1 over R naught. And then our initial temperature is a constant, so that derivative is just 0, right? So now we look at this, or sorry, this is R, and we want to relate it to Ohm's law, right? So what is Ohm's law? I'm going to move this over. Right. So what is Ohm's law? Ohm's law is our change in voltage equals our current times our resistance. Well, how do we relate that? Before, we used Fourier's law, right? We have our Q equals or minus Ka dt dr. Great. Let's use Fourier's law again. So what is our area? That's the big question here. So when we look at this, we have our circle. We have our circle. Well, the area of a circle is 2 pi r, right? Our radius is here, right? So when we look at Ohm's law, it's just Q equals minus K 2 pi r. And then dt dr we found down here is our C R over R naught, or R final. Wait, yeah, this should be an R final. No. So this actually should be R naught over R, and this is an R naught. All right, we plug that in. We have our R naught over our R times our 1 over R naught. Well, our R naughts cancel, and our R's cancel. So we're left with Q equals minus K 2 pi C. Well, we know what C is, right? That's just our term here. So we're at T final minus T initial over ln R final R initial, right? Well, we relate this. This is what we're looking at, right? So our change, that relates to our delta V, right? So when we look at this, we know that our Q from before is our current. So what does that leave us with, right? So we rearrange, we get delta T equals Q times ln R final over R initial times 1 over 2 pi. But since it's 2 pi k, but since we're in cylindrical coordinates, there's actually a height associated with this area. And so our final equation relating to Ohm's law is our change in temperature equals our heat times the natural log of our final radius over our initial times 1 over 2 pi thermal conductivity times our height. And that is everything.